Hi, I'm Dr. Groh, and this is Differential Equations, Lecture 10. In our last lecture, we talked about Laplace transforms, and in particular, we showed that the Laplace transform can be used to undo derivatives in the following way. Here, we suppose that capital Y is the Laplace transform of the undifferentiated function little y. We also showed how this applies to the second order derivative, undoing both derivatives here, and these formulas can be generated for nth order derivatives. As an example, for an application of these formulas, consider the differential equation y double prime plus 2y prime plus 10y equals 3 e to the minus t, with initial conditions y of 0 equals, let's say 1, y prime of 0 equals 2. So we are initially displaced and moving. This is a forced harmonic oscillator with resistance and a spring constant. We apply the formulas that we've just shown. Applying the Laplace transform to the second order derivative, we'll have s squared y minus s times 1 minus 2. That's the Laplace transform of y double prime, plus twice the Laplace transform of y prime, which is s times big Y minus 1, plus 10 times the Laplace transform of y. All of that must equal the Laplace transform of the right-hand side, which is 3 divided by s minus negative 1. Collecting all of the y's together, we end up with big Y times s squared plus 2s plus 10. We need to put all of the other terms onto the other side of the equation. We already have 3 over s plus 1 on the right-hand side. This term brings an s plus s to the right-hand side. Here we have a negative 2, and here's another negative 2, for a total of negative 4. When it goes to the right-hand side, it is plus 4. Completing a square here, you can see that this is going to be s plus 1 squared plus 9. We'll divide this off, yielding y is 3 over s plus 1 squared plus 9 plus s plus 4 over the quantity s plus 1 squared plus 9. To proceed, on this first term, we need to perform a partial fraction decomposition. In that form, it's probably easier to just write this as s squared plus 2s plus 10. On this term, we need to split this so that we have an s plus 1 in the numerator. I'll break the 4 into plus 1 plus 3. That way the first grouping can be split off and the second grouping be split off by itself. For the partial fraction decomposition, we'll write 3 over s plus 1 times s squared plus 2s plus 10, which is an irreducible quadratic, as a over s plus 1 plus bs plus c over s squared plus 2s plus 10. Clearing the denominators gives 3 is a times s squared plus 2s plus 10 plus the quantity, don't forget the parentheses here, bs plus c times s plus 1. If we set s equal to minus 1, so that this entire second part becomes 0, we get 3 equals 1 minus 2 is negative 1 plus 10 equals 9a, or a is 1/3. The next reasonable choice for s is s equals 0. If we choose s equals 0, we get 10a. That's 10/3 plus c times 1, which is just c. 3 is 9/3. If we subtract the 10/3 over, we get c is negative 1/3. We'll put these in buckets. The next reasonable choice for s is one that gives us as few computations as possible. Why not s equals 1? In this case, we get 3 equals 13a. That's 13/3 plus b plus c, that's b minus 1/3 times 2. In this case, you have a negative 2/3 and 13/3 gives you 11/3, which you move over and combine with the 9/3 on this side. 9/3 minus 11/3 is negative 2/3 divided by 2. You get b is negative 1/3. It follows then that the Laplace transform of the solution function to the differential equation is 1/3 over s plus 1 minus 1/3 s minus 1/3 plus s plus 1 plus 3 over s plus 1 squared plus 9. We'll rewrite this as 1/3 over s plus 1 minus 1/3, we'll factor the 1/3 out of the numerator here. That leaves s plus 1 over s plus 1 squared plus 9 plus, we have an s plus 1 over s plus 1 squared plus 9 plus 3 over s plus 1 squared plus 9. We can combine like terms. Here we have a 1 of this expression minus 1/3 of that same expression. 1 minus 1/3 leaves you with 2/3. We're now set to solve the differential equation by taking the inverse Laplace transform, recovering the solution function, little y. Taking the inverse Laplace transform term by term, from here we will have 1/3 e to the minus t. This term gives us plus 2/3 e to the minus t cosine of 3t. Perhaps you can see why I wanted you to memorize some of these formulas. Plus the inverse Laplace transform of the last term. That's just e to the minus t sine of 3t, giving us the solution to the initial value problem. Okay, I know what you're thinking. This method for solving this initial value problem is much more difficult than the methods that we've already derived. Why not just find the solution to the corresponding homogeneous equation using the characteristic equation, and then use either the method of undetermined coefficients or variation of parameters to solve the non-homogeneous problem. Substitute the initial conditions in to determine the constants C1 and C2. Easy as pie. The reason is we are going to introduce forcing functions that are going to complicate matters, and we will not be able to solve these initial value problems using those forcing functions. In particular, we're going to introduce forcing functions that are discontinuous. Now I want you to think about that. We want to be able to introduce forcing functions that are discontinuous because we want to be able to model flipping a switch on an electrical circuit. We want to be able to have something to be on and then off, or off and then on. And the suddenness of that change will take place at a particular instant in time. Our solutions to these second-order equations, you would think, would have to be 2 times differentiable. That won't be possible with these discontinuous forcing functions. But it gets worse. Not only do we want to model the flipping of a switch, we also want to be able to model hitting something with a hammer, an instantaneous force, a force that applies over such a small time frame. We're going to be modeling this by a force that happens at an instant in time. That may seem impossible, but we're going to find a way to do it. And not only that, think about the effect on your second-order differential equations. How can you have these impulsive forces and yet second-order derivatives on these solutions? And you simply can't. So the methods that we applied earlier will be insufficient for handling these new situations. These situations you want to be able to model because you want to be able to apply, say, a spark to a circuit, or you want to model something that happens instantaneously, like hitting a cymbal with a drumstick, and you have the oscillations of the cymbal being modeled after some impulsive force. Say you want to model an explosive charge on the ground that sends sound waves down through the ground and then bounces off. That explosion is a force that happened on the surface of the ground at an instant. And so how do you model the effects of that if you want to, say, use these to model that propagating sound wave through the ground? Another example might be you want to model the introduction of a species into an environment. So first it's not there, then it is there. What happens under those circumstances? There are myriad applications to these discontinuous forcing functions and impulsive forcing functions. And we won't be able to solve those with the methods that we've derived already. We will require some kind of integral transform, and we will apply the Laplace transform to this purpose and completely solve those problems. There's another objection that you might have. In our formula, the Laplace transform of y prime is s times y minus y of 0. It implies that the initial data must occur at t equals 0. A lot of initial value problems might require that the initial data be at some other point. How then do we model these other cases? Well, it's not that hard. If I make a substitution, let's suppose that I'm solving some kind of an initial value problem, of this form, t naught equals y naught, y prime of t naught equals y naught prime. All we have to do is change the independent variable. Suppose we set x equal to t minus t naught. Then whenever t is equal to t naught, x is equal to 0. What is more, dx dt is equal to 1, which means that dy dt is dy dx dx dt, where dx dt is simply 1. Also, the second order derivative of y with respect to t is the derivative with respect to t of dy dt. We've already seen that dy dt is dy dx. We can rewrite this as, say, dx dt the dx of dy dx. And this gives us 1 times the second order derivative of y with respect to x. Our initial value problem then can be re-expressed using x instead of t. The initial value problem is transformed on the right-hand side. Recall that x was t minus t naught, so that t is x plus t naught. We'll have x plus t naught substituted into the function of f. We'll then have y of 0 equals y naught, because when t is equal to t naught, x is equal to 0, and also y prime of 0 equals y naught prime. I'd like to build up the reason that we're doing this now. And in particular, I'd like to talk about the unit step function. The unit step function is denoted by, we'll say, UA of t, and is defined by, it is 0 for t values less than a, and 1 for t values greater than a. What happens at a, we don't particularly care. Some authors will define the value to be the average of 0 and 1, the average at the endpoints, which makes some sense in the context of Fourier transforms, which we're not doing here. So for us, what happens at a single point, as far as these discontinuous forcing functions is concerned, will be irrelevant. It won't make a difference. There's another notation that is common. If we just write u of t, that's often taken to be the unit step function with the discontinuity at t equals 0. In this case, UA of t can be described as just a translation of ut. The Laplace transform of the unit step function at a can be found using the definition of the Laplace transform. Now, since the unit step function is 0 until you get to a, we may as well pick up the integral at a. After t equals a, on this interval, the unit step function takes the value of 1. And so we just have dt. Evaluating the integral, finding an antiderivative, we have negative 1 over s, e to the minus st. Assuming that s is greater than 0, when we take the limit as t goes to infinity, this first term will be 0. We'll subtract what we get when we plug in a. That's going to be negative 1 over s, e to the minus sa. And finally, that gives us e to the minus as divided by s. One thing to note, if a is 0, then e to the minus as will be 1, and the Laplace transform will be 1 divided by s. That's exactly the Laplace transform of the function that is identically 1 over s, which this function will be on the relevant interval from 0 to infinity. So this is consistent with prior results, but a generalization of it, allowing for the function to be 0 until you get to a, and then 1 thereafter. Laplace transform of the unit step function at a is e to the minus as divided by s. You need to remember that. Just to emphasize the result that we just had, I'll codify it as a little theorem called a lemma. the Laplace transform of the unit step function at A is e to the minus as divided by s. Before getting to applications, I need a little theorem. The hypotheses of the theorem are this. If f is, let's say, piecewise continuous and of exponential order alpha greater than 0, and the Laplace transform of little f is big F, then the Laplace transform of ua of t, f of t minus a, notice this is translated a units to the right, is e to the minus as times the Laplace transform of little f untranslated. We're going to use this two ways. We'll use it this way, but we'll also use it this way. When we take the inverse Laplace transform of e to the minus as f of s, the effect of this exponential factor e to the minus as is to put a step function and to translate the original function over. This is going to be the primary way in which we will use this identity. To prove this, let's consider the Laplace transform of ua of t, f of t minus a. The only thing we have to go on is the definition of the Laplace transform. So we're going to write this as the integral from 0 to infinity, e to the minus st, ua of t, f of t minus a, dt. Now, again, because the step function is 0 until you get to a, you may as well start your integral at a. And in that case, after a, u is 1, and so you just get f of t minus a dt. At this point, we make a substitution. We'll set u equal to t minus a, and hence du is dt. I'll put this in a box. The integral becomes, notice that if t is equal to a, then u is equal to 0. And as t goes to infinity, u also goes to infinity. We have e to the minus s, t is replaced by u plus a, we'll have f of u du. Now, we're going to break up this exponential as e to the minus su, e to the minus sa, f of u du. Now, this factor does not depend upon u, so this can be brought out of the integral. And this is just the Laplace transform of f. So we get e to the minus as times the Laplace transform of f, and that is the end of the proof. Let's suppose that we have a simple harmonic oscillator with no resistance and a forcing function that is 0 until t equals 1 and 1 thereafter. So we're flipping a switch at t equals 1. This is initially undisplaced and not moving. To solve this problem, we'll apply the Laplace transform to both sides of the differential equation, giving s squared big Y minus 0s minus 0 plus big Y. On the right-hand side, we'll have e to the minus as, a in this case is 1, divided by s. Factoring y out on the left-hand side gives y times s squared plus 1 equals e to the minus s divided by s. Taking this factor and dividing it off, we have big y is e to the minus s over s times s squared plus 1. We need to perform a partial fraction decomposition on that right-hand side without reference to this e to the minus s. That'll just be a factor we'll multiply on to both of the terms after the partial fraction decomposition. To perform the partial fraction decomposition, note that s squared plus 1 is an irreducible quadratic. So we have to write this as a over s plus bs plus c over s squared plus 1. Multiplying both sides by the denominator on the left-hand side yields 1 is a times s squared plus 1 plus the quantity bs plus c all times s. If we combine like terms on the right-hand side, you can see that you have a bs squared and an as squared. That's a plus b times s squared. You'll have c times s, and then the only constant term is a. A fact about polynomials is one polynomial equals another polynomial if and only if corresponding coefficients are equal. We deduce that the constant terms must be equal, and hence a is 1. The coefficient of s on the right-hand side is c. The coefficient of s on the left-hand side is 0. We have c equals 0. And then the coefficient of s squared is a plus b. That has to equal the coefficient over here, which is 0. We get a plus b is 0. Since a is 1, b is minus 1. We have then that big Y is e to the minus s times 1 over s plus negative s over s squared plus 1. We can see then that if we take the inverse Laplace transform of each side, we'll have a unit step function multiplied by this 1 over s. We have e to the minus s over s minus e to the minus s over 1 s divided by s squared plus 1. The first term has an inverse Laplace transform u1 of s, u1 of t, minus u1 of t cosine, but the cosine is translated 1 unit to the right. I'd like to think about how this function looks. Is this function going to be discontinuous or is it going to be continuous? Let's evaluate. I'd like to think for a minute about this function y equals u1 of t minus u1 of t cosine of t minus 1. And in particular, in reference to the identity sine squared of theta divided by 2 is 1/2 1 minus cosine of theta. If we factor u1 of t out, we'll have 1 minus cosine of t minus 1. That's almost like the right-hand side here. To make it exactly like the right-hand side, we need a divided 2 here, and we'll pay for it with the 2 out front. And so this gives us twice a unit step function times the sine squared of t minus 1 divided by 2. So this function is off until t equals 1, and after that it starts a pattern like this. If this is 1, it does nothing until it gets there, and afterwards it takes off like this. Note that the function is continuous at t equals 1. To determine whether or not this function has a continuous derivative, we might calculate y prime as follows. This will give you nothing. It'll be flat. The slope will be flat, 0, until t equals 1. So we still have 2u1 of t. It's a question of what the derivative is over here. You'll get twice sine of t minus 1 over 2 times the cosine t minus 1 over 2 times the derivative of the inside, which is 1/2. This 1/2 will cancel this. To the rest of this, we may apply the double angle identity for sine. That's equal to u1 of t times the sine of t minus 1. You can see now that at t equals 1, the sine of t minus 1 will have a value of 0 because the sine of 0 is 0. So the slope is 0 until you get there, and when you get to that spot, it takes off with a slope of 0. So perhaps I've drawn this a little more severely than it should. It takes off with a slope of 0 and then pulls up. It's non-negative everywhere, though. We're now ready to discuss what happens with impulses, namely the Dirac Delta function. The Dirac Delta function is not a function, as you will see. In fact, it's a class of things called generalized functions. And we have to define the Dirac Delta function in terms of integrals, as you will see. We want to model a force of some measurable value that occurs at one particular point. To do that, what we're going to do is we're going to look first at little bumps, little square waves, little digital signals. Suppose I have UA of t minus UB of t. This is like a switch that is off until A, where it jumps up to a height of 1. We're subtracting what happens if we flip another negative switch at B. So this is going to be 1 until you get to B. Once you get to B, it's 1 minus 1, bringing it back down to 0. In this way, we can model a digital square wave. Now, suppose we want to model a wave centered at A, starting at A minus epsilon to A plus epsilon, in such a way that the area of this is 1. Notice that the interval here is 2 epsilon wide, which means if we want to get an area of 1, this has to be 1 over 2 epsilon tall. So if we integrate from, say, 0 to infinity, we'll suppose 0 is here, so A is way out here someplace, and A minus epsilon is still greater than 0. If we have 1 over 2 epsilon times UA minus epsilon of t minus UA plus epsilon of t dt, you get 1. Intuitively, which means what I'm about to write is nonsense, we want our force to be some measurable value 1. This is the lowercase Greek letter delta. It stands for the Dirac Delta function centered at A. We want that to be equal to 1, the area under the curve, but we would like the Dirac Delta function to be defined in such a way that you get 0 when t is not A, and infinity when t equals A. All the force is located at one point, all the area is located under one point of the curve. This is, of course, nonsense. To make sense of this, we'll make the following definition. The integral from minus infinity to infinity of the Dirac delta function at A times some other function is, by definition, which means because I said so, so you're just going to accept what I write next. The limit, as epsilon goes to 0, we will have 1 over 2 epsilon u a minus epsilon of t minus u a plus epsilon of t all times f of t dt. So the Dirac delta function is determined by a limit of this kind of window function, if you will, a digital pulse of height 1 over 2 epsilon. As epsilon goes to 0, the heights of those little peaks, those little windows will go higher and higher, and the width will get narrower and narrower. Before we do a lot of computations, I would like to point out that if we take the integral from minus infinity to infinity of a Dirac delta function times some other function, you get the function evaluated at A, provided f is continuous in a neighborhood of A. This is pretty easy to prove. The proof requires the mean value theorem for definite integrals. So to prove this, I suppose we should review the mean value theorem for definite integrals, which says that a continuous function on a closed and bounded interval attains its average. There's a point C between A and B where the average height is equal to the height of the function, but the function f must be continuous on the interval AB. Continuous functions on closed and bounded intervals attain their average. This is how you calculate the average height of a function. With this in mind, we'll proceed with the integral. This is, by definition, the limit as epsilon goes to 0 of the integral 1 over 2 epsilon, and then the difference of the two step functions and we can bring the 1 over 2 epsilon out, and what is more, the function here has a height of 1, but only between a minus epsilon and a plus epsilon. So we'll get the limit as epsilon goes to 0 of 1 over 2 epsilon, but only from a minus epsilon to a plus epsilon, and between there this is 1, and so we get f of t dt. This is an average. If I take b minus a, I get 2 epsilon, so this is 1 over b minus a, the length of the interval that we are integrating over. If that's the case, by the mean value theorem for definite integrals, I must get the limit as epsilon goes to 0 of f of c, where c is between a minus epsilon and a plus epsilon. So c is trapped between these two walls at a minus epsilon and a plus epsilon. And as epsilon goes to 0, these walls collapse around a. They come together when epsilon gets to 0 at a. Since c is trapped between a minus epsilon and a plus epsilon. And since epsilon is going to 0, c must tend to a, the point in between. We see then that this limit is exactly f of a, and that completes the proof. Next, we need to know what the Laplace transform of the Dirac Delta function is. Well, we will prove that this is e to the minus as. That's pretty easy to see, because if I just calculate the Dirac Delta function, I get the integral from 0 to infinity of e to the minus st delta a of t dt, and by the last theorem, since this is a continuous function everywhere, you just evaluate that function at t equals a. And now for an example. Suppose we have ourselves a simple harmonic oscillator, and we strike this thing at t equals 2 with an amplitude of 3. This is initially undisplaced and unmoving. Then we apply the Laplace transform to both sides. This is like a symbol, by the way. A simple harmonic oscillator. We strike the thing at t equals 2 with an amplitude of 3. We've applied the Laplace transform to both sides, so we get s squared y minus big Y equals 3 e to the minus 2s. On the left-hand side, oops, this is plus. On the left-hand side, we can factor out the big Y and then divide this over. We get big Y is 3 e to the minus 2s, 1 over s squared plus 1. Now, from our experience with step functions, we know that the exponential function e to the minus 2s, when we calculate the inverse Laplace transform, will lead to a step function, and it will translate the inverse Laplace transform of everything else. Taking the inverse Laplace transform, we deduce then that the solution to this impulsively forced simple harmonic oscillator is 3 u2 of t. The inverse Laplace transform of 1 over s squared plus 1 is the sine of t, but we have to translate that. We get the sine of t minus 2. The picture of the solution is like this. Until t equals 2, nothing happens. Once we get to t equals 2, we start a sinusoidal oscillation with an amplitude of 3. Note that we have a little corner here. So while the solution function is continuous, the solution does not have a derivative at t equals 2. The derivative should be discontinuous there. The second order derivative has an impulse. It must have a delta function source, since the differential equation ended up having a delta function forcing function. I want to think about what we've just said about this last solution a little more. Suppose I have a differential equation which has a delta function source, and I'll assume that y of 0 equals 0. This is a simple initial value problem, and what we're really asking here is what function has derivative equal to this impulsive function, which we modeled as something that's 0 everywhere except at one point, and at the one point it's infinite. We can solve this using Laplace transforms. Taking the Laplace transform of y prime, we get sy minus 0. On the right-hand side, we get e to the minus as. If we divide both sides by s, we get the Laplace transform of little y is e to the minus as divided by s, and hence the solution y is the unit step function. Let's think about that. from what we've just shown, the derivative of the unit step function is the Dirac Delta function. The unit step function looks like this. Until you get to A, it does nothing. After you get to A, it has a height of 1. What is the slope of this function? Well, the slope is going to be 0 on the left and 0 on the right. The only place where you get something undefined is at t equals A, where the slope appears to be infinite. And that kind of matches the model here for our slope of being 0 until you get to A, being infinite at A, and then 0 afterwards. It's fascinating to see that the derivative of the unit step function is the Dirac Delta function. I think you can see why the Dirac Delta function is not really a function. It's not really legitimate to say that a function is 0 except at one place, and at that one place you get a value of infinity. Infinity is not defined. We can only define such a function in terms of limits involving integrals. Let's do another example. Let's suppose that we have y double prime plus 2y prime plus 10y equals, on the right hand side, I'd like to put something like 3 delta 1 of t. Let's suppose that y of 0 is 1 and y prime of 0 is 2. Taking the Laplace transform of each side, we get s squared big Y minus s minus 2 plus 2 times s big Y minus 1 plus 10 times big Y equals 3 e to the minus 1s. We collect all the big Y's together. We have a coefficient of s squared plus 2s plus 10. We have an s here which needs to be brought to the other side. We have a minus 2 and another minus 2 for minus 4. When we bring that to the other side, we get plus 4. We now divide both sides by the quadratic. It follows that y is 3 e to the minus s over s squared plus 2s plus 10 plus s plus 4 over s squared plus 2s plus 10. The denominator, if you complete the square, you divide the coefficient of s by 2 and square. That'd be s squared plus 2s plus 1, which is a perfect square. We'll have to split this 1 off, and that gives s plus 1 squared plus 9 in the denominator. We'll do the same thing over here. And now we see that the numerator would better be better if it were s plus 1 and not s plus 4. We'll have to split this off, and so that we can write this as big Y is 3 e to the minus s. This 3 goes nicely in this spot here because the square root of 9 is 3. Then we have an s plus 1 plus 1 squared plus 9 plus 3 over s plus 1 squared plus 9. Finally, taking the inverse Laplace transform on each side, the first term gives us a unit step function at 1. This part gives rise to an e to the minus, because you take the opposite sign here, and it's translated 1 unit over t minus 1. There's a sine function going on here, the sine of 3 times the quantity t minus 1. So this part results from the delta function dinging this oscillator at t equals 1. The other two parts arise from the initial data. This part is e to the minus t cosine 3t, and the last part is e to the minus t sine of 3t, giving you the final solution to the initial value problem.